This is the first lecture covering differences between groups analyses, particularly t-test and ANOVA. And this first one I'm going to be covering some underlying principles behind the t-test and the ANOVA before we begin actual lecture material. So these are the things we're going to be covering in this series. First of all, when to use the statistic of a t-test and ANOVA. Looking at issues of independent versus paired samples. You should know what that means by the end, which goes within or between design. Those two things are related. Bullets number 2 and number 3 there. You should be able to define all the terms that I discuss in this lecture. You should be able to calculate a degree of freedom. It's a very simple calculation, I promise. Any second grader can do it. You should understand the idea of power applied to t-test and ANOVA. You should understand why it's not a good idea to do multiple t-tests. And you should understand the difference between a one-tailed and a two-tailed test. You should be able to understand the assumptions that are affiliated with each of those statistics, the t-test and the ANOVA, how to report the statistics, when to use different statistics assumptions, so which assumption applies to which, and then the nuances around those assumptions. What do the numbers mean when you're reporting them? How do you interpret them, particularly what an F ratio is? And then some follow-up options of ANOVA, when and what kind of follow-ups would you do for ANOVA. So first of all, we are in the categorical independent variable and continuous dependent variable part of your statistics map. So if you think about a larger statistics map, and those of you that are creating a portfolio that are in my class, that kind of takes the whole of statistics and kind of tries to create a map out of it. This is thinking in terms of your independent variable, predictor, is categorical, and your continuous variable or your outcome variable is on continuum. So here are our objectives. I just went over some of those. It's the same thing. So we are primarily looking at differences between groups and trying to determine if those differences are with the probability of p.05, if those differences are caused by the independent variable, or if there's not a difference between the groups. So an example we can use in this, is there a difference between using Prozac and using the new drug ketamine in the treatment of depression? And you have their two mean scores. Let's say that higher numbers mean less depression, just to confuse us all. So higher numbers means more happiness, and people that, or more change, people that have Prozac, they are 6.58, and people that have ketamine have a mean score of 9.77. So, does that mean that ketamine is better than Prozac? Because you got a higher number there. How do you know if those two groups, the ketamine group and the Prozac group, are significantly different from each other? Well, this is the statistic that's going to answer your burning question. And this is a really interesting question, by the way. There's some side research on ketamine going on right now, and keep an eye on it for the future on what's going to happen with pharmacology. So what should Dr. Williams do if she's doing this research? She has two independent samples. All right, notice the word independent there, highlighted, meaning that the behavior in one sample is not related to the behavior in the other sample, meaning she probably randomly assigned a large group of people into two groups here. Right? And they are independent, meaning if you're in one group, you're not in the other group. You're only in one group. So you're either getting Prozac or ketamine, not both. She could run an independent samples t-test to compare the two means and see if they are significantly different than each other. Right? So let's relate this back to designing a hypothesis around this. What would her hypothesis be? So you might stop this video for a second and try to come up with your hypothesis. And the answer is there a significant difference between ketamine and Prozac in depression scores, or happiness scores, as this might be phrased as, right? There could be a null hypothesis, which would mean there's no difference between the groups, and the alternative or research hypothesis would be that there is a significant difference. All right, what she's actually doing with her categorical IV and her continuous DV is comparing the distribution of one group with the distribution of the other group, right? To find at what point is there a critical value where the differences are improbable as a function of chance. So you see here at the bottom of your screen, you've got two very poorly drawn bell curves. One is for Prozac and one is for ketamine. So if everyone who took ketamine, they're going to fall on a bell curve, right, of how happy they are, right? Some people are going to be super happy and some people are going to be kind of on the low end of happy, and a lot of people will be bunched up in the middle. And for everybody taking Prozac, the same thing. You'll have a bell curve of your sample all spread out. And so if you take those two bell curves, you could actually move them. You could actually make them kind of go back and forth there. And if you could put them right on top of each other, and then it would be very clear that there's no difference between them if they have this same exact mean score and the same variance. There's no difference between them. And then if you start to spread them out and pull them further and further apart, there comes a point at which if the data looks like that it's not chance that's causing the difference between these two bell curves, that there actually is a cause of it, and we would assume with our research, if it's done well, that the cause is the medication. Right? Something that you have to remember is that it's not just the mean scores. This is very important. These three sets of bell curves here, have the exact same mean scores. Right? If you look at the bottom one with the low variability, you'll see that those two hardly overlap with each other at all. Right? There's very, very little overlap, maybe just a couple people down there in the middle that are kind of in between that blue and green section. But for the most part, these two groups are really quite separate from each other. They have low within group variability and high between group variability. That's a really important concept to understand. Okay? The top group has medium variability with the two groups. They have medium level of within group variability, and some that they have the same between group variability, right, as the other groups. All three groups have the same between group variability, meaning their mean scores have the same difference. But what happens with that middle group is the most interesting thing. If you look at it, the two groups are overlapping with each other. Those two bell curves overlap at such a high level that it will be very difficult for someone to know which group someone was in based on their score, because there's such a high variability within each group. So this is demonstrating to you a very important point for both t-test and ANOVA, and that is what you need to get a significant difference between groups is high between group variability, meaning that the mean scores are far apart, right? And you need low within group variability, like that bottom one where everybody's all clumped together, right? With this nice leptokurtic type of curve there. If you have a platykurtic curve, like you see in that middle picture in front of you, you're never going to be able to tell which group people are supposed to be in because there's really not much difference. And you're not going to get a probability of p.05, and you'll just be sad because it's hard to publish things that aren't significant. So this is just a very important point about exactly what is happening behind the scenes whenever you're doing a t-test or an ANOVA. So it's very important to understand that we are looking at differences between the two groups, and we have to judge the difference between their mean scores, which is between group variance, relative to the variability or the spread, the within group variance of the scores. A t-test can do that, and ANOVA can do it too, but we're going to be covering the t-test first here. So make sure that you understand this concept of what we're looking at is not just the mean differences between the two groups, right? It's not that you just look at the mean scores and tell, oh, those two groups are different because their mean scores are 5 points apart or something. It really doesn't matter completely what the mean score differences are. That's one part of it, but the variance is extremely important as well, how much variance you have in the groups. So we are comparing two groups' means and variance, but remember, each group will have its own sample size. And it's not always equal because of the way things work. The rat died, the person decided to quit in the middle of your study, something happened, and you can get different dropout rates, if nothing else, in, say, your two groups. So you're going to have different samples. in the groups. One denotation I want you to remember whenever you're looking at articles or reading things or understanding how things work in this profession, and that is a capital N is a denotation for the total number of participants in all of the groups, and a lowercase n is indicating the number of participants within one single group. So if you have 50 people in the ketamine group and 50 people in the Prozac group, your capital N is 100 and your lowercase n would be 50. If you had different numbers, say you had a dropout and your ketamine group had 49 while your Prozac group had 50, then it would be N, capital N equals 100, and you'd have to have two separate numbers reported. Lowercase n ketamine is one number, lowercase n Prozac is a different number. So those are, when you're reading articles or you're presenting your own data, making sure that you use that capital and lowercase correctly. Okay, this is a formula. Don't fall apart. It's really not that bad, and I'll just kind of walk you through it as we go. First of all, you see up here that this is the mean score, the X, right? So X with a line over it means the mean score. And the letters, the T and the C, indicate which variable or which group you're working with. So that would be like the ketamine group and the Prozac group. We probably would do K and P for those, right? But this example used a T and a C. Right? So these indicate, so that's the mean of one group minus the mean of the other group. So really all that is the difference between the means, right, on top. Very simple, right? That's between group difference right on top. Now that's over, and we are looking at the variance for this group over the number of people in that group plus the variance of the other group over the number of the people in that group, and you square root it. And by doing that, you kind of standardize it. And so we have basically on top, we have the between group variance, and you'll notice on the bottom, we have within group variance being examined. So you've got a ratio of between group over within group variance, and that gets you what your T value is. Right? So if nothing else, you need to understand it's between group on top and within group on the bottom. All right. So this gets you to your degrees of freedom, and this is an important concept that I know a lot of students struggle with, so I want to try to walk it through. The degrees of freedom depends on the number of values in a set of score that are free to vary after certain restrictions are placed on the data. So if you have a mean score of something, and if you sum up all the differences between each score in a study, and that mean score would always equal 0, right? So if we take everybody's score and the IQ test, and then we add it all up, and we take the mean score for our group of people, right, our IQ mean for our class, and then we look at the differences. Some people will be above the mean, some people will be below the mean, and don't make negative comments about yourself right now. Watch your self-talk. Always be positive. Everybody is good at everything, right? No, everybody's good at something and what they're supposed to be good at. So, but back to the topic. There would be the differences score would add up to 0. Okay, so because that's true, right, because the differences score between everybody in the group and the mean is always going to be calculated up to 0, and because we can assume that, right, then no matter how many scores we have, we can always figure out the final one because of that. So if we have 5 scores only in a study, and you tell me what the mean score is, so we always know that, 4 people can give me a score, right? Doesn't matter what those 4 numbers are, but once those 4 numbers are locked in and given, the 5th number has to be a certain thing, because when you add up the 4 numbers, they could be any numbers, but when you do the final number, it must be that missing number, right, to fill in the formula, essentially, because of the degrees of freedom being true. So this is kind of the mathematical reason for it. It's not super important to understand that, except just to understand that degrees of freedom kind of tell you how much freedom you have within your numbers. They also give you a hint at how many participants you have in your study. So n minus 1 tends to be, lowercase n, you'll notice, minus 1 is the formula that you're going to need to know. Let me walk us through this a little bit more with an example. If the mean of a set of just 3 variables, okay, is 11, right? There's an infinite number of options to get to that mean. You could have 11, 11, 11, right? And that would be a mean of 11. You could have 10, 11, 12, and that would have a mean of 11. There's an infinite number of 3 numbers that would add up to a mean and have a mean of 11. Now, if you say one of those numbers is 7, then you still have an infinite number for the other 2 numbers. If you say one number is 7 and the other number is 10, you are now locked in, right? It's kind of like Final Jeopardy. You put in your answer, and you can't change it now, right? There's only one possible value for the third number. So for this problem, with 3 collected variables, there's 2 degrees of freedom. Once 2 numbers are determined, then the third number is fixed. All right. For your portfolio, I want you to make sure that you understand what degrees of freedom is and how it would be calculated. So if you have a mean shoe size of 8 in a class and a frequency distribution of 5 people and they have shoe sizes of 2, 5, 11, and 10 there, then the 5th person's shoe size has to be what? And how many degrees of freedom is in this problem? I'm going to give you the answer, at least on the degrees of freedom right now. I believe you can add up the answer to that other question, but the degrees of freedom answer is 4, because you'll see once you have 4, right, 4 numbers can vary, but once you have 4, that 5th one is locked in. You'll notice a pattern here with this, right? If you have just one group, which is what we've been talking about, just one group we're looking at, then the degrees of freedom is always the number of people in that group minus 1. Well, that's so much easier than having to calculate it the other way, isn't it? But at least you understand what that number means, right? And in fact, if you have a degrees of freedom, you can go backwards with it and figure out the number of people in your group, right? Because it's just going to be the degrees of freedom plus 1 is going to tell you how many people are in that group. And that's really nice and helpful to be able to look at data and know what the sample size is without having to report the n. And in fact, that's what most articles in psychology do. They don't actually report the n's for each group. They just assume that you'll pull it out from the degrees of freedom that is reported. All right, and this is just a fun thing to end this part of the lecture, and that is an interesting side story. The inventor of the t-test, which we're about to talk about, Gossett, in 1899, was motivated because he was brewing beer for Guinness in Ireland, and he wanted to know what kind of barley to use to make the produce more consistent. So he would do 2 different kinds of barleys, and he would compare them, and he would run t-tests on them to see which one was better, and just keep doing batches of 2 and comparing the 2 batches. And he used the pseudonym student. You may have heard it called the student t-test in the past. So Guinness wouldn't have to own up to the bad batches. So if he wasn't concerned about that, it might have been called the Guinness test, which would have been just very interesting, I think. So, all right, hang on for another lecture in a minute that's specific to t-tests.